Okay, next up, let's talk about the domain name system. The best way to take a look to think about the domain name system is in the concept, the fact that um, just like people have different ways to identify themselves, so do internet hosts and routers. So basically, a person is usually commonly identified by their name when talking with other humans, but um, there's usually some sort of ID number that is assigned to each one of us, whether it's a social security number or a passport number or what have you. Um, and that concept um, is also true of internet hosts. It's obviously easier for humans to refer to a host by some sort of host name, but that host name really needs to be um, translated into a unique address, and it's usually the IP address, whether it's an IPv4 or IPv6 address. And we're going to basically focus on IPv4 addressing and talking about the domain name system. So basically, the reason for the domain name system to exist is to do that translation or that mapping between human understandable host names and IP addresses. So basically, the domain name system is a hierarchical distributed database um, that lets you have access to different name servers at the end of the hierarchy tree, have the information that lets you do that final mapping from names to addresses. And the domain name system has been around for a long time, and so it uses a very simple tree structure, and it's commonly used around the world. It's pretty established, and so we're going to talk about the details of how that works. So basically, from the point of view of talking about application layers, the domain name system is an application, also uses its own application layer protocol that lets hosts and name servers communicate with each other to resolve these names into IP addresses. So, and this is one of those areas where the layers get a little fuzzy, because basically it's actually an internet level function, but it's implemented as an application layer protocol. So basically, as we said, DNS basically translates host names to IP addresses. It has the ability to do what we call host aliasing. So hosts have their canonical names, which is their real name, but they also have their alias names. And you can see, you'll see this a lot when we do the Wireshark lab of, what the real canonical names are for a lot of actual hosts, and it's a lot more complex than the simple CNN.com. Mail servers themselves have special aliases as well that the DNS keeps track of. DNS services are also set up to allow for load distribution. So basically, when you say you go to CNN.com or Yahoo.com or Amazon.com or Google.com, that name can be translated into very specific web servers. So you can have multiple web servers that can service one particular name. And like I said, this is really illustrated very well in the Wireshark lab, where you can see how a particular CNN.com might, that's just basically an alias, and the canonical name can be multiple servers, and those can be correspond to multiple IP addresses, and then it's up to the person that's, or the system that's controlling those web servers to put out which particular host is going to actually respond to a CNN.com request. And like I said, this is a distributed, very elegant database. It's not centralized, which wouldn't make sense. First of all, that would be a single point of failure. That would kind of basically bring the whole internet down if there was some centralized DNS server. And a centralized server couldn't handle the traffic volume. And then also you'd have, since this is global, you'd have the problem of having the distance. If you were too far away from the centralized DNS, would take too long to make connections. And then who is going to maintain a centralized maintainer would mean somebody have to get some sort of bill to do basically a lot of work. So this is how DNS is set up. There is a root DNS server. You have to go to the top of the tree structure to the root, kind of very similar to how the Unix operating system and file structure is set up. Then under the root DNS server are the major your major servers, the .com, DNS servers, .org, .edu, etc. And each of those servers point to particular servers under them. So the .com DNS server points to, say for example, the Yahoo and Amazon.com DNS servers. The .org DNS server points to the pbs.org, and edu DNS server points to the poly.edu and umass.edu DNS servers. So let's say a client wants the IP address for www.amazon.com. They would go to the root server to find the .com DNS server, and the DNS server would .com DNS server would query the Amazon.com server and get to provide the address, the specific IP address that's going to be used between your host and Amazon.com. So basically, this actually shows you where there's more than one root name server. In fact, a lot of them very centralized in the United States, but there's basically 13 root name servers worldwide. Of course, this balances out the network traffic, so it doesn't take forever to do your name resolution. So basically, you're going to contact your local name server, and then your local root name server, and that's going to contact the authoritative name server under it. If it doesn't know the mapping, then it gets the mapping and returns it to the local name server. And we're going to see there's two main types of methods to get that information. But basically what this shows you is you have 14 root name servers, and each of them have multiple physical sites around the world. So under your root name server, you have what's called your top-level domain servers. These are your com, org, net, edu, jobs, museums, etc., as well as all your top-level country domains such as UK, the United Kingdom, FR for France, CA for Canada, JP for Japan, etc. So Network Solutions is the company that maintains servers for the .com top-level domain. Educause is the company that maintains the edu top-level domain. Okay, below those Top-level domain servers are the authoritative domain name servers. They are each organization's own DNS server providing authoritative host name to IP mappings for an organization's named hosts, and they are either maintained by the organization itself or by the service provider that the organization uses. So, for example, UMass Dartmouth uses either maintains its own umassd.edu domain name server, or the service provider for UMass Dartmouth maintains that server for UMass Dartmouth. I actually don't know which of the two that it is. It's one of those two cases in this particular example. Then you have your local domain name server. So this does not strictly belong to the hierarchy. This is kind of below that level, and you'll see an example of that. Each ISP so has its own, it's also known as a default name server. So when a host makes a DNS query, the query is sent to the local DNS server, and it has a local cache, and the local cache has recent name to address translation pairs. They may be out of date. There's basically some settings that determine how often that gets updated, and can act as a proxy and forwards queries into the hierarchy. So this will make more sense as we go through this. So there are different ways to do name resolution. You have your iterative. Oops. Okay, I think I just crashed my computer. All right, here we go. You have your iterative and you have your recursive queries. So let's take a look at the iterative. Whoops, that's not what I want to do. Hold on a second. We can do this. Let's walk through this first. So imagine that you have a host at cis.poly.edu, or that's some university, and it wants to get the IP address at gaia.cs.umass.edu, and that would be the UMass Amherst location. So basically, one way you can do that is to do an iterated query. And in that case, you contact the server, and the server replies with the name of the server to contact. So this assumption, because keep in mind, each of these domain name servers do maintain information, but let's say that the time to live on this information is gone, and so we have to go through the whole process of working through the name servers to get the answer. So we start off with our querying our local domain name server. The local domain name server queries the root domain name server that gives us the top level domain name server information. It gets that information, then it has to go to the authoritative domain name server, which is the domain name server at dns.cs.umass.edu. and then finally we have all the information, and we can speak to the get the IP address from the host. So basically, to kind of walk through that, our local DNS server says, I know where the root is, so I get the information for the root. The root says, I know where the .edu top-level domain is. I'll give you that information. The top-level domain says, I know where to get to the authoritative domain name server, and then that authoritative domain name server actually has the IP address for gaia.cs.umass.edu, and it basically finally sends that to your host. So that's an iterative query. Next we have the recursive query. So in the recursive query, I talk to my local host and I say, I need to get to gaia.cs.umass.edu. The local host knows where the root is, so it goes to the root, and the root says, well, I know where the top-level domain for .edu is. It gets that information from the top-level domain. And top-level domain server says, I know where the authoritative DNS is, so it gets that information. The authoritative DNS says, well, I know the IP address of gaia.cs.umass.edu. It passes that to the top-level domain, which passes that to the root, that passes that to the local DNS, and you finally get your answer. So basically the burden shifts of where the communication occurs. So in this case, our local DNS have to do a lot of work. In this case, all these guys, in the case of recursive, all the work is basically shared amongst all of the DNSs in the path. The advantage for recursive is it gives all of these DNS servers the ability to store the information locally with some sort of time to live. So those are two different methods. So, like I was saying, once the DNS has information, it learns that mapping. It caches the mapping. It basically stays until some timeout value, which is a time to live, and then it has to get refreshed. Top-level domain servers are typically cached in your local name server, so very rarely do you have to go to the root name server. A cached entry may be out of date, and if the host name changes IP addresses, it might not be known internet-wide until all times to live expire. So if something happens and you have a host, the host goes down, and the IP address change may not propagate right away throughout the network. So because of this, these times to live are often not set too high. And this whole mechanism is defined in RFC 2136. So basically, keep in mind that DNS is basically a database. And so it basically has fields, and the fields have values. So the DNS stores what we call resource records, and resource records basically have 4 fields: name, value, type, and time to live. There's some examples of a type of resource record. Could be a type equal to A, where the name value is going to be the name is going to be a host name, the value is going to be the IP address. If the resource record was of type NS, for name server, name is going to refer to some sort of domain, and value is going to be the host name of the authoritative name server for that particular domain. So these values are going to vary based on the type of resource record. If the type is a CNAME, standing for canonical name, the name is the alias for the canonical name. For example, when I want to reach www.ibm.com, the real name to www.ibm.com might be servereast.backup2.ibm.com. So this allows the IBM.com name to actually be associated with multiple real hosts with different names. It just gets translated based on what's in your local DNS. And there are also specific resource records for mail servers. Usually mail servers have like a mail, looks like a mail dot. So let's say like a mail.servereast.backup2.ibm.com. Usually mail is inside that name. So MX record has a value of the name mail server associated with a particular name. So this basically shows the types of messages that are sent across DNS protocol, across the DNS protocol. So like we said, every time protocols have different messages with different message formats. So this shows if you had in the Wireshark lab, you should be able to see this type of information go across the wire. So basically, DNS will have a query and a reply message. Both the query and the reply message will have the same message format. So basically, the messages are we'll have a message header, which will have a unique identification number. Used both for the query and the reply to the query uses that same identification number, so they can be linked. You have different flags. A flag will determine whether it's a query or a reply to a query. We can determine if we want to use recursion or iteration by setting query can say I want to use recursion, and we come back with a response that recursion is available. If not, you're going to use an iterative query instead. And whether or not the replier is authoritative, that basically means that it's coming from the authoritative name server, not from something higher in the hierarchy. Okay, so once we get past that, we actually have the actual information in the message. You will have the in here the name and the type fields for a query. So basically, this is the information that I'm looking for. When you respond, the domain name server will respond with resource records that are in response to that query. It will also have records for authoritative servers, so this can point to an authoritative server, as well as some additional information that might be helpful. So let's see, here's an example. So we want to talk a little bit about how this works. So there are actually organizations that actually get the information into the DNS. So, for example, let's say you had a new startup company called Network Utopia. You have to, and you're going to be using the .com domain, so you want to register your name as networkutopia.com. So you have to go to your DNS registrar. As we mentioned earlier, Network Solutions manages a .com domain, so you have to go to them to register your name. Once it's officially registered, you're going to provide the names and IP addresses of your authoritative name server and get that into the system. So the registrar will insert 2 resource records into the .com top-level domain server, and it's basically going to be your basically linking your networkutopia.com to DNS1 networkutopia.com, which is going to be your authoritative name server, and then another record that's going to link your authoritative name server with its actual IP address. So it's going to be basically create an authoritative server type A record for networkutopia.com, and not shown here, it'll also include a .mx record for the mail server for networkutopia.com if you're going to have a mail server associated with that as well. So at this point, we're going to stop and take a break, and then we're going to continue with additional lectures.